Assalamualaikum warahmatullahi wabarakatuh. Today our group will be presenting about our project which is lemongrass harvesting tool. We are from section 4 group 7. Okay, now let me introduce my team. My name is Muhammad Amirul Bakhtiar bin Jamaluddin, number matric A8241100, and there's Muhammad Akil Hazil bin Muhammad Hafiz A8241111, and lastly Muhammad Alif Naufal bin Shukri A8240205.
Next, I would like to get into our introduction. Okay, for the subtopic 1.1 is our background of study. For this project, we focus on lemongrass harvesting in Malaysia. Lemongrass is widely used in food, essential oil, and also for medicinal purposes. However, most farmers still use traditional tools such as sickles and hoes. These tools are not designed for those lemongrass roots and require repeated manual force. Lemongrass also needs to be harvested frequently, around every 60 to 70 days. This causes fatigue, discomfort, and high stress on both the user and the tool. Because of this, an improved manual harvesting tool is needed. The design must be analyzed using solid mechanics to ensure it is strong, safe, and efficient.
Moving into the problem statement, it is important to understand why this project is necessary. While lemongrass is a high value crop essential for oils and culinary markets, we are still relying on generic and optimized manual tools such as sickle, hoe, and soil chopper, which is not specifically designed for the unique toughness of lemongrass stalks. The biggest issue here is the human cost. Manual harvesting requires repetitive cutting and stoop posture. As you can see in the image, the farmer is bent over, which lead to chronic fatigue and musculoskeletal disorder or MSD. Over month and year, this significantly reduce the productivity and well-being of the farmer. From an engineering perspective, current tools are failing. They experience high bending and shear force with every poor load distribution. This weak structural design doesn't just lead to tool damage, but it create safety risk for the user and result in low operational efficiency. This brings us to our primary objective, which is developing an improved harvesting tool. By applying a rigorous solid mechanic analysis, we can create a design that optimizes force distribution, reduce physical strain, and ensure long-term durability.
Next, I will get into our project objective. The first objective is to design a manual harvesting tool that can increase efficiency and reduce the physical effort compared to traditional methods. Second is to analyze the stress and strain acting on the main components of a manual lemongrass harvesting tool. Third, to determine the shear and bending moment on critical parts of the tool. Fourth and lastly is to propose a safer and stronger tool design based on solid mechanic analysis. Next is our project scope. The project focuses specifically on the harvesting of the lemongrass. Evaluation of main components such as the handle, frame, cutting blade, and foot pedal. Stress, strain, shear force, bending moment, and torsional analysis under basic static loading. It is also focused on simple, low-cost design suitable for small-scale farmers.
Okay, now to design a better tool, we first have to look at the current state of the art and the nature of the crop. Lemongrass is a labor-intensive crop. The first harvest happens around the 90 day, with subsequent harvests every 60 to 75 days. For the highest quality essential oil, we aim for the pre-flowering stage because the window for optimum quality is so specific, speed and efficiency are vital. As it stands, traditional harvesting relies fully on human physical labor. It involves a punishing cycle of repetitive cutting, digging, and uprooting. This requires high upper body strength and result in long working hours, which quickly leads to operator fatigue. When a farmer gets tired, the harvesting becomes improper, which can damage the stalks and roots, directly hitting the farmer bottom line by lowering crop quality. Okay, if we look at the tools currently in use, we see three main culprits, which is the sickle, hoe, and soil chopper. We will talk about the sickle first. Common for cutting, but it requires a high repetition risk and arm motion that is a leading cause of strain. And number two is hoe, used for uprooting. It's made of heavy iron and depends entirely on impact, force, and using strength. And the last one is soil chopper, While it uses a hardened steel blade, it still requires a vertical impact driven by the upper body.
Next is flowchart of the project implementation. This slide shows the flowchart of the project implementation. The project starts with problem identification and concept design. Then material selection and structural analysis are carried out. If the proposed design meets the design criteria, it will be selected as the final design. If it does not meet the criteria, the process will return to the concept design stage for improvement. This flow ensures the final product is safe, functional, and also very efficient.
Alright, now I will talk about the proposed solution. Our new harvester is a big change from the old ways. While the traditional soil chopper used just arm and shoulder strength, our design use full body weight. It lets the user use their legs and gravity to do the hard work, which is much easier on the body. The biggest difference is how we apply force. Instead of swinging a heavy tool, the farmer just step on a foot lever. This put all the pressure exactly where it's needed. By using a smaller blade edge, we make it much easier to push into the ground with every little effort. We also improve the shape and strength of the handle. Instead of a basic stick that might snap, we use a hollow bar design that is very hard to bend. We also added extra strong weights at the joints to make sure the tools doesn't break at the spot where it feel the most pressure.
Next, I will get into the technical specification based on the final sketch of the product. For component blade angle, the specification is it needs to be 30 to 45 degrees for its sharpness to be optimized for easy soil penetration. Next is the main shaft. Its specification is hollow steel. Its technical benefit is high strength to weight ratio, which is high moment of inertia. Third, joint type. It is reinforced fillet well. It prevents fatigue at high stress concentration points. Lastly, the loading. The specification is vertical eccentric. For the technical benefit, converts full body weight into cutting pressure. Okay, meanwhile, this slide explains the design stages of the project. First, before this, we need to do a final sketch of the product that is prepared based on the design concept. Next, free body diagrams are drawn for each component based on this slide. Okay, point A represents the foot peg where the main load is applied and the maximum bending moment occurs. Point B is the main shaft that supports the entire structure. Point C is the blade where soil reaction force acts. These stages help us understand how forces are distributed throughout the tool.
Okay, to make sure the tool is safe, we start with some basic. We assume the user weight is 80 kg, which is about 785 Newton of force. We choose mild steel because it is strong, slightly flexible, and very reliable for farm work. We look at the stress, which is basically how much pressure the metal feel. Under a full load, the normal stress is only 3.63 megapascal. This is very low for steel, meaning the tool won't stretch or deform when you use it normally. Since the farmer steps on the side pack, the tool has to resist bending. Our math shows the bending stress is about 85.73 megapascal. Okay, we also check torsion, which is just the twisting force when the farmer wiggles the tools to loosen roots. The twisting stress is very slow, only 7.28 megapascal, so the handle is more than strong enough. Finally, we calculated the factor of safety. This is a score that tells us how much extra strength the tool has. Our score is 2.92. This means the tool has almost 3 times stronger than it needs to be. It builds to last and won't break, even if a heavy user steps on it and or hits a hard rock.
Okay, so now I will be presenting about the component of the project. Okay, for the first one, which is the top handle that allow handed grip for better control, help stabilizing the tool during digging. And for the second one, it's the vertical pipe, which maintain the user posture and reach. It also resists bending and buckling during soil penetration. And for the third one, which is the footstep, which allow user to apply body strength to penetrate the hard soil. And for the fourth one is the mm, blade shaft or the solid connector to the blade, which transfer bending and shear forces from blade to handle. And lastly, the blade, which penetrates soil during digging operation and cuts through compact soil and roots.
For material selection, different components use different types of steel. The top handle and main handle use mild steel because it is easy to fabricate and has good strength. The footstep also use mild steel to support body weight. The blade shaft and blade use medium carbon steel. The blade is heat treated to increase hardness and wear resistance. This material selection ensure the tool is strong, durable, and suitable for agricultural use.
Okay, so now for the final proposed design. So there is three things here, which is the final design, the simulation of stress, and the simulation of displacement. Okay, now for the analysis, our group is using SolidWorks simulation. The material for this project is IC1020 steel, which is strong, tough, suitable for agricultural tool. As you can see, the maximum stress, and we can see that the stress is smoothly distributed with no critical concentration, and the maximum stress is far below yield strength. For the displacement, the you can see the maximum displacement and the minimum displacement of this tool. So the deformation remains within acceptable limits. And for the conclusion, it is high factor of safety and the design is structurally safe and suitable for manual lemongrass harvesting.
In conclusion, this project has successfully fulfilled the primary objective of designing a manual lemongrass harvesting tool that enhances operational efficiency while significantly reducing physical effort compared to traditional hand pulling methods. By shifting the power source from manual arm strength to the user body weight through a foot pedal mechanism, the design effectively minimizes musculoskeletal strain on the farmer. The structural integrity of the tool was rigorously verified through stress and strain analysis, confirming that all main components, specifically the handle and the hollow steel frame, operates well within the elastic region of the material. This ensured that the tool remains durable and safe under repetitive static and impact loading conditions.
So that's all from our group. Thank you.